first column. So I get 1 times the subdeterminant, and that's all it is. Because 0, who cares what it's multiplied 0, right? 0 over here.
Okay. Oh, I get you.
Okay.
Because as you go.
Yeah. So
to
you
the
do
other.
the 1, knock out that row in that column, and get a 2 by 2. Here it is, right over here, right?
Right. Okay, I got you.
And that you do that times that minus that. Everyone has to know the 2 by 2. Right?
Yeah.
Okay. Okay. Again, I'm not going to belabor this because it's not, something that's required really. Yeah. Again, I hate all these definitions, but they aren't necessary. And again, try to motivate this a little, but it doesn't really do that too well. Okay. What we're going to basically define shortly is something called a fundamental solution set. Fundamental solution set. Obviously, the word seems to say something fundamental, right? And what it is basically is that it's going to be a set of functions that will be able, by taking linear combinations, to generate any solution of the differential equation. Again, let me go back to my example of the XYZ space again. All right? Everybody introduces a unit vector I cap along the Y, a J cap along the Y, and a Z cap along the Z. No, K, right? Different books use different things, right? I assume your calculus used IJK, that's what's most common. Okay. And the idea is that any arbitrary vector V in this space can be written as Xi plus Yj, in order to be consistent, J cap plus Z times K cap. And all I need is 3. I don't need any more, and any less will not do, right? If I throw away the unit vector K, if that's not in my discussion, all I can do is a linear combination of I and J. They'll give me a vector in the XY plane. So I need these 3. Do I need, for example, IJK and I plus J minus K? No, it's redundant, right? To get any point, space only has 3 degrees of freedom, so to speak, and IJK will be sufficient. And this is the idea now. We're trying to transition this type of idea of expanding an arbitrary vector to 3 space in terms of functions, okay? I have a differential equation, let's say it's of order 2. How many solutions do I need in order to get all solutions from that? To come out, it works nice. It's just like this. It's going to be 2. If it's a second order, if it's a third order equation, you'll need 3. Fourth order, you'll need 4, etc. Okay. And this is what's called a fundamental solution set. Let me try just to define the way the book does. Okay. So this is a definition. Okay? So, a set of functions what I should do first, I'm going to put this on the board in red. Remember I said you can always use this L notation, okay? So that, let's go back over here. Okay. L operating on Y. Right? These places of n of x. Remember this, you can use this again and again. Plus, and then we have a1 of x, b1 dx. This is the most general linear equation. Okay, plus a0 of xy equals some function g of x. Okay, that's again, to remind you, that's the form of the general nth order linear differential equation. Okay? That's the most general form of a linear nth order equation. Again, it's nth order because what's the highest derivative? Nth derivative of y with respect to x. Okay? And again, I'll remind you, if g of x is non-zero, it's called non-homogeneous. G of x equal to 0, not there. Identically 0 is called homogeneous. And what we're going to do is first discuss the homogeneous equation, because as we'll see, that's a critical component of solving the non-homogeneous equation. And if you had linear algebra, it's the same thing, right? You had ax equals b. First you solve the x equals 0, then you talk about ax equals b. Okay, so whenever you see L operating on y, just go, it's this red thing over here. So we don't have to write it over and over again. Okay, so a set of functions, let's call them y1 of x, comma y sub 2 of x, dot, dot, dot. Let's say there are n of them, y sub n of x, is termed or called a fundamental solution set. This is the new vocabulary. if two conditions are satisfied. L operating on yi of x is equal to 0. That's just a fancy way of saying what? Each of those individual functions, little y1, little y2, solves a homogeneous equation. Okay? And 2, the set of y's, you know what I mean by that, y1, y2, are linearly independent in some interval, obviously, right? Okay, so basically for a set of functions to qualify as a fundamental solution set, two things have to be satisfied. Each of the functions individually has to solve the homogeneous equation, just put the right-hand side equal to 0, and they better be linearly independent. Now, is a fundamental solution set unique? No. Just like when I go over here and I do ijk, that's convenient because they're orthogonal. I can do, if I'm crazy about it, but it could be, I can say let the vectors be ij and k minus I plus 3j. There's still 3 independent vectors and they span 3-dimensional space, okay? Over there would be kind of weird. You want to take functions which are orthogonal to do that, okay? In differential equations, it's sometimes you can, but in most cases you can't, or it's not practical. So we'll be happy with having a set of functions that are linearly independent, and each of which satisfies the homogeneous equation. Okay. Okay. Now comes that result, which I've been promising you, which is going to be very easy to prove actually, is that I'm going to show you that any, and by any I mean underline, any solution of the differential equation, of the homogeneous equation, L on y equals 0, will always be expressible as any combination of the fundamental solution set. So let's just write that down and prove it. Okay, it's very simple. Okay. Notice that so far I haven't said how to get these independent solutions, okay? That's the topic of, next few classes that we have. But we have to have this theory in practice so we know what to do. So when you're encountered, for example, in the strength of materials course with the 4th order differential equation, you know, oh, I've got to get 4 independent solutions before I can even start on the thing, okay? So that's why you need at least a little bit of the theory so it doesn't, otherwise it just doesn't make any sense. It's very hard to remember. So hopefully, I'm trying to get a reasonable balance, so to speak, between theory over here and practical, okay? I don't want to just throw stuff at you, but again, I realize that most engineers are interested mostly in solving problems, okay? But sometimes we have to go through some of this rather painful, painful is maybe too strong, but maybe a little boring for some people. Okay. So here's the theorem basically, and the proof is going to be very simple. Every, and I'll underline that, solution to the homogeneous differential equation and what is that? L on y equals 0. And again, until you get used to this, always go back to the red. What's he talking about over here? Every L on y is 0. It's this equation over here, right? A(n) of x, n to the root of y respect to x, plus dot, 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 all the way down to 0y equals 0. Notice I put 0 on the right. That's called homogeneous. And what's really powerful about that is I said nothing about the functions, the coefficients over here. They can be any arbitrary functions of x. You recall the existence uniqueness theorem, though, did require them to be continuous, okay? And also this guy did not vanish. And as the book will do, I'm not going to mention that anymore. We're going to assume that that's the case, okay? That all those coefficients are continuous so that there is a solution exists. Okay. So what does this theorem say? Every solution of the homogeneous differential equation, L on y equals 0, can be expressed as a superposition or a linear combination, same thing, of the fundamental solution. That's a pretty powerful result. okay? So if somehow, and this is what we're going to be concentrating on now, again, we haven't done this yet, but if somehow if you have an nth order differential equation, okay, and you can construct n linearly independent solutions to that equation, what this theorem claims is that any solution to that equation is just a linear combination of y1, y2, multiplied to that. Okay? And actually the proof is not difficult at all. Go through the proof over here. Okay, the way that these proofs kind of an interactive thing, okay? So you got your equation over here, and let's say somehow you were able to come up with n independent solutions. You got your y1, your y2, y7 of x. Someone comes up to you, okay, someone else in the class, they say, I have a solution of that homogeneous equation. Okay? Let's call it big Y of x. Your challenge now is to be able to express his big Y of x in terms of your little y's, because that's what the theorem says. It says, you give me any solution to that homogeneous equation, I can always write as a linear combination of this fundamental solution set. Okay, proof. So let cap Y of x be any solution to the homogeneous equation, which is what? L operating on big Y of x is equal to 0. Okay, so it gives you this big Y of x. You verify, yeah, it's a solution to the homogeneous equation. Okay. If this theorem is true, then I should be able to find coefficients, C1, C2, Cn, so that this big Y of x is a linear combination of those. Okay, so need to find C1, C2 down to C sub n, such that this homogeneous solution that you were given is just C1 little y1 of x plus C2 little y2 of x plus plus C sub n little yn of x. Right? If I can show that I can find these c's so that this big Y is expressible like that, then I've proven the theorem, right? Every solution, it claims, of the homogeneous equation can be expressed as a linear combination of those. Okay, so far we say, okay, here's the challenge now. Someone gives a function big Y of x, it's a solution of the homogeneous equation. I have to be able to find c's such that his big Y of x is a linear combination of my fundamental solution set. Okay. Well, the first thing you want to do is check that it's a homogeneous solution, right? We know that his big Y of x is a homogeneous solution. This thing better be a homogeneous solution, right? And that's easy. What's L operating on C1, Y1 of x plus C sub 2, Y2 of x plus C sub n little yn of x? Okay? By linearity, it's C1 L operating on Y1 plus C2 L operating on Y2, right? Plus C sub n L operating on yn of x. Remember, that was just a property of a linear operator. Okay? But by definition, my little y1, y2 are what? It's a fundamental solution set, and a fundamental solution set, they all satisfy the homogeneous equation, by definition. Okay? So therefore, all these guys are 0. Right? 0. Therefore, the L on y is indeed equal to 0 if I express it like that. Okay? So at least that's the case, right? So I know at least that, yeah, if I take a linear combination of my fundamental solution set, it satisfies the homogeneous equation, and that's a necessary condition if this is to be true. But that's not enough, right? Because I can come up with some other C's that maybe will do it. What makes the C's unique is the following, okay? He gives you a function big Y of x. Suppose it's x squared sine x plus e to the x. Just think of it as a concrete function. That function, because it's given to you, you'll know its value at some point is called x naught. You'll know its derivative of x naught. All those things you can calculate because he gave you y of x. Okay? That's where the challenge is to come out to get the c's. Okay? But we know, because y of x is given, we know y at some point x0. Okay, we know y prime of x0, right? All the way down to y n minus first derivative at x0. Those are known because he gave me y of x. Okay, so let's plug in those known initial values for big Y of x and see what that says about our little C1, C2. Well, since
Quick
big Y of x is given, let's plug in x equals x naught. We find C1, Y1 of x naught, plus C sub 2, Y2 of x naught, plus C sub n, Yn of x naught, that's given. Big Y of x 0. So the right-hand side, this is a known number, okay? Y1 of x naught is known, Y2 of x naught is known, the C's are unknown. So now we're getting constraints on these C's, you know? Yeah.
Okay, what is above, before we know y of x naught, what does that say? L of y
Over
equals
here?
0?
Oh, yeah, sorry. Yeah, L1 big Y is 0. It checks. Or let me put it, yeah, I should say it this way. You see how we wrote big Y? We said we could write it in this form, right? Big Y is a solution of the homogeneous equation. All I did was verify that, yes, the right-hand side satisfies the homogeneous equation. So L on big Y of x does come out to be 0, as we, must have, okay? Okay. So, now, basically, but you see that works for any value of C's. I can take arbitrary values of C's over here, having nothing to do with the value of big Y at x naught, its first derivative, and it'll still satisfy the homogeneous equation. I have to show that I can reproduce the big Y of x exactly, okay? And I know Y of x naught, okay, because big Y of x is given to me, it and all its derivatives I can just get by differentiation. So that's one equation on the C's. I also know the derivative of big Y at x naught. That's specified. So that says C1 Y1 prime of x naught. Right? Just take this equation and differentiate. Plus C sub 2 little y2 prime of x naught plus C sub n yn prime of x naught. That's given as y prime of x 0. So remember, all this stuff is given. The left-hand side, the C's are unknown. And I'm going to go all the way now. Let's go now to the very last initial condition. That involves what? Big Y of x n minus first derivative of x naught. That's given. So now when I differentiate n minus 1 times, I get y1 n minus first derivative of x naught plus C sub 2 y2 n minus first derivative of x naught. Okay? Plus C sub n little yn n minus first derivative at x naught